Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start this lecture, and still welcome to today's lecture. And one thing I need to remind you that is that assignment 1 is due tomorrow, and it's at 11 a.m. in the morning, not 11 at night. And also only hard copy submission is permitted, so you cannot send me an email about your assignment 1 and say that you have already submitted your email, because only hard copy submission is required. And any questions about assignment 1? Okay, no question. So let's continue the topic. And in the previous lecture, I think I talked about the multicollinearity. And I think I mainly talk about the concept and also this flowchart about how to deal with the multicollinearity. But I talk about the real example very quickly, so I will repeat the real example a little bit. So basically, for the problem for the multicollinearity is that some explanatory variable xj can actually be approximately expressed by using other explanatory variables. And accurately speaking, this variable xj can be approximately linearly expressed by using the other variables. So in order to identify this problem, we propose a statistical measure, which is called VIF, to measure this kind of problem. So the definition of VIF here is that the VIF can be expressed by 1 divided by 1 minus Rj square. So Rj square is the R square, but it's the R square if we regress xj on the other variables to measure whether or not xj has a large linear relationship with the other variables. So if xj has a very large linear relationship with the other variables, then in this case we should have a very large Rj square. And if we have a very large Rj square, we're going to have a very large VIF. So that's the idea behind the VIF to identify the multicollinearity problem. Basically, we use VIF to measure the linear relationship between xj and the other explanatory variables. And the standard, the rule of thumb standard here is 10. So if VIF is larger than 10, then we say that we actually have this kind of multicollinearity problem. So if we have the multicollinearity problem, so that means one explanatory variable xj can be expressed by the other variables, and then we can result in this two series problem. The first problem here is that maybe beta hat, which is our estimation, cannot be computed because when we compute the beta hat, we actually need to compute some matrix inverse. But if we have the multicollinearity problem, the matrix inverse cannot be computed. So that's one problem caused by the multicollinearity. And the second problem here is that even if sometimes this matrix can still be computed, but the standard errors of the estimations are very large. So in that case, the estimation is not accurate and stable. So in that case, we always have the insignificant result. So usually in your real application, you need to find some significant explanatory variable to predict the response variable. So if you have this multicollinearity problem, you always have the insignificant result. And in that case, that is actually not good for your real application purpose. So that's the reason why we need to solve this problem. So in order to solve this problem, we introduced the backward elimination idea by using this flow chart. So the idea is very similar, but we consider a little bit different criterion A and also criterion B. So I'm not going to repeat it again, but I'm going to use the real example to repeat the procedure to solve the multicollinearity problem. And I think in your assignment 2, I will assign a question for you to solve the multicollinearity problem by yourselves. So firstly, in this real example, we still consider the SAT data. We want to use some explanatory variable to predict the SAT score. So the response variable is still the SAT score, so which is y. And we regress y on the other, all the other explanatory variable. So we use this y tilde dot, and we specify the data set of the explanatory variable as x. So that means we want to regress y on all the variables in this data set. And then we can have a look at our result. And this is the summary output. And I think you should be familiar with that. And that is the output with all the variables. So the next question is that now we have the regression with all the variables. And we need to answer this question that whether or not we have this multicollinearity problem for these explanatory variables. So we have 1, 2, 3, 4, 5, 6. We have 6 variables in total. So we want to see whether or not we have the multicollinearity problems for these 6 variables. So how can we do that? So in order to find the multicollinearity problem, firstly, we need to install this package, which is called CAR, C-A-R. And after you install this package, what you can do here is just to use this library function to load this package, and then use the function VIF. VIF just means vector inflation factor in this case. And also, you need to use the output of the, I think this is actually the summary output. Summary output, I think. This is actually the summary output. Summary function output. So you need to put the summary function output inside the VIF function in order to get the VIFs for all the variables. And then what you can do here is just to start the procedure of dealing with the multicollinearity problem by using this flowchart, but we need to transform this flowchart into the R codes and also R output. So here we have 6 variables in total. So what we can do here is that we start the backward step for 6 variables. So in this flowchart, we have the backward step for k variables. Because in total, we only have 6 variables, so we start this step. And in this step, what we need to do here is that we need to use the criterion A, if you remember, to determine whether or not we should eliminate one variable from this 6 variable. So what's the criterion A for this multiple collinearity problem? So the criterion A here is that if we use this VIF function, if we find that some VIFs are larger than 10, then we should continue, otherwise we stop. So in this case, because after we use this VIF function, we find that actually there are 2 variables whose VIFs are larger than 10. So we determine to continue. We determine to continue here, and we need to consider which variable we should eliminate. So that's our criterion B. So how can we determine the criterion B, so which is which variable we should eliminate? So based on this result, we know that these 2 variables, takers and rank, they both have the multicollinearity problem. So we need to determine which variable we should eliminate. So let's just have a try. So the first option here is just to eliminate takers. So here, eliminating, we use this square bracket -1. -1 just means we eliminate takers. We eliminate one column in this data matrix. So that means we eliminate the first column, which is actually represents the takers variable. And in that case, we have this new data matrix without this variable, and then we try the linear regression, and also we can look at the linear regression result without this variable by using this deviance function. So using this deviance function, we can obtain the sum of the squared error, which measures the goodness of fit for this modeling. So we can find that dropping this takers variable, we have this SSE1. Or we can try to drop rank. So -6 means we eliminate the 6th column of this data matrix. So that means we drop rank variable. And in that case, we can also get the sum of the squared error by dropping this variable in the regression. So that's our sum of the squared error 2. So in order to determine which variable we should eliminate, we actually need to find the smaller sum of the squared error, because the smaller the sum of the square is, the better fitting of a model. So in this case, this is our smaller sum of the squared error. So in that case, by using this criterion B, so criterion B basically means to find the smaller sum of the squared error, and we determine to drop takers. And after we drop takers, we only have 5 variables. So we start the backward step for 5 variables. So after we start this step, so basically we repeat something similar. Firstly, we need to use criterion A to determine whether or not we should stop or continue. So in this case, what we can do here is just to have a look at the VIFs of these 5 variables. So fit 1 is actually the fitting after dropping takers. So after we drop takers, we only have 5 variables left. And if we have a look at the VIFs for these 5 variables, 1, 2, 3, 4, 5, and we find that we no longer have this VIFs larger than 10 problem, or smaller than 10. So in that case, we should stop. So that's actually from our criterion A. And we get our conclusion. So our conclusion here is that by using the backward elimination step, we solve the multicollinearity problem, and now we only need these 5 variables. And if we only use these 5 variables, we no longer have the multicollinearity problem. So that's how we use R in practice to solve this multicollinearity problem. So basically, I think the important thing here is actually this kind of flowchart. And this flowchart is exactly from the more complicated flowchart here. So I think in your assignment, I think I will assign a question for you to be more familiar with this kind of procedure to solve the multicollinearity problem. Any questions? Okay, so if there is no question, so we can take a very brief 1-minute break, and then we are going to start a totally new topic about logistic regression. Okay, let's start this new topic about logistic regression. So I think in the first half of this semester, we mainly talk about the continuous response regression, which is our multiple linear regression model. And in the second half of this semester, we are going to talk about the discrete response variables. But we are going to start from this very simple and basic 2-category response variables. And then we are going to talk about how to regress on this kind of categorical response variable. So you can treat the second half of this semester as the generalization of the multiple linear regression model. So in other words, which is called a generalized linear model. And this is the outline of this topic. So in this topic, we are going to talk about what's the meaning for this 2-category response variable, and also we are going to give an example to motivate us to consider a new modeling instead of the classical multiple linear regression model. And then we are going to introduce this new model, which is called binary logistic regression model. And usually after we talk about a model, we are going to talk about estimation. And I think the structure here is similar to the first lecture of multiple linear regression model or the first lecture of the simple linear regression model. And finally, by using this model, we can actually predict this kind of 2-category response variable, and we will briefly mention the prediction of this new modeling. So you can have a look at those references. So firstly, let's talk about this new data type. So for this new, it's actually not a new data type, because if you remember, when we talk about categorical explanatory variable in multiple linear regression model, we have already seen this kind of categorical variable. For instance, the gender, if you still remember, gender has 2 categories. The first one is male and the second one is the female. So in a lot of applications, we can consider this kind of categorical variables taking 2 values. So usually for this kind of categorical variable, we can consider to use this binary indicator variable taking on the values of 0 and 1 to represent these 2 categories. So I give 2 examples. The first example here is that in this study of advertising, So we can consider this variable whether or not a customer is willing to buy the new product. So we can consider this response variable y equals to 1 if a given customer is willing to buy. So and 0 if not willing to buy. Or in this another example, we can consider y equals to 1 if the individual owns a home. 0 not owns the home. So I think you should be familiar with it because we just use an indicator variable to represent two categories. I think that's nothing new. But the new part here is that we treat this as a response variable. So we are going to predict whether or not a customer is willing to buy some new product, or we are going to predict whether or not an individual owns a home. So that's the difference. Now we are considering using this kind of two-category variable as our response variable. So that's the difference compared to the multiple linear regression case. Because for multiple linear regression case, we have already solved the problem by using this two-category variable as the explanatory variable. But we have never talked about how to consider to use this two-category variable as a response variable. So this is the difference. And when we consider it as the response variable, usually it is from our empirical study. So for instance, in our empirical study, we just want to predict it. And later I'm going to use an example. We are interested in predicting it, so we treat it as the response variable. So this is our motivating example. We consider that we have 30 customers, and they were given a particular length of the advertising in seconds. So for instance, some promotion agent can talk to those 30 customers for maybe 1 second, 2 seconds, or 30 seconds. Or they can actually play a video of advertising in seconds. So basically, these 30 customers were exposed to some certain advertising in seconds. And after they watch the video, or after those customers talk to the promotion agent, and there is a questionnaire for them to ask whether or not they are willing to buy the product or not. So here, the response variable here is 1 if the customer was willing to buy the product, and 0 otherwise. So that's our data set. Understanding the background. So let's have a look at our data set. So this is the data set. So we can see we have 30 customers. And for these 30 customers, we have their responses. So responses equals to 1 means the customer was willing to buy the product, and 0 means the customer was not willing to buy the product. And also we have the length or the time of advertising. So we have this kind of different situations for the advertising. So the first one here is that we are trying to see after 1.25 seconds of advertising whether or not the customer is willing to buy a product. So we have a lot of different situations of the time of the advertising. So here, let's just have a look at the feature of this kind of data. So firstly, for the response variable, we only have 2 values, 1 and 0. So that's the most important feature for this binary logistic regression. So that means we only have 2 categories for this response variable. And secondly, we can actually compute something by using this data set. So what we can compute? We can compute if we treat time as x and response variable as y. So given each value of x, for instance, x equals to 1.25, we can compute the number of y equals to 1, given this kind of category. Given x equals to 1.25, so the number of y equals to 1 equals to 1, 2, 3, 4, 5, 6, right? 6. And also we can compute, given each value of x, we can actually compute the sample mean of y. So how to compute it? So what we need to do here is that we just add those 1 and 0 and obtain and divide, and we use the summation and divide it by 7, because in total we have 7 observations. So 1 plus 1 plus 1 plus 1 plus 1 plus 1, 2, 3, 4, 5, plus 0 divided by 7. And then we are going to have 6 divided by 7, right? So that's the sample mean. And also, we can compute the sample variance, but we are not going to compute here by our hand, and we are going to compute it later. And also, we can compute something which is called the proportion of y equals to 1. So, because the number of the y equals to 1 equals to 6, and the total number equals to 7 in this specific case, so the proportion just equals to 6 divided by 7, right? So in this specific 1-0 response variable case, the proportion is exactly equal to the mean. So remember something here for the binary response, mean equals to proportion. That's actually from our observation of the data. Because it's an proportion, so then we have this very important observation here that proportion is within 0 and 1, obviously. Because for this kind of binary variable, the mean is exactly equal to proportion, so that means mean can only be within 0 and 1. So that's the most important feature for this binary response variable. So we can get this conclusion that mean of binary variable can only be within 0 and 1, right? Because we only have 1 and 0, and the mean here is exactly equal to the proportion. You can also compute the other kind of categories. You can try given x equals to 1, or you can try x equals to 0.833, or you can compute the other kind of cases. You can always find this kind of conclusion. So the mean of the binary variable can only be within 0 and 1. So that's the feature of this kind of the data. So remember this feature, and then let's try to use our classical regression model. So try to look at the classical regression model to see what will happen if we use the classical regression model. If we use, so this means what will happen if we use ML, multiple linear regression model. So in order to obtain the multiple linear regression model, so what we need to do here is just to use the regress response variable on time. So that's the classical multiple linear regression model. But I think there is something new in the code here. We use this attach A. Attach A just means that after you use this attach A, you can directly use the variable name. So that just means after attach A in R, you can use time directly. So in that case, you can use time directly. Remember that if I think in the old examples, we do not use this attach A. We always need to use a $time to call a column in this data set. But the best thing for this attach A here is that after we consider this attach A in R, and then we can just use some variable directly without specifying $. So that's just sometimes makes it convenient. So by using this fit, which is the LM function output, which is the LM function output. So I think I mentioned something wrong in topic 9. So this fit is actually not summary output. It's the LM output. So sorry about it. So the fit is actually the LM function output. So I need to correct the handwritten notes, I think, at the beginning of today's lecture. But we can still look at the topic. For the topic 10, we also have the LM function result, which is called fit. And we can use this lines function to draw a dashed line for this fitted line. So this is actually our fitted regression line. So this is the fitted regression line by using this lines function. And LTY equals to 2 just means we get this dashed line. So that's the meaning for this line of the code. So basically in this plot we have our observations. So our observations are basically 0 and 1, right? Because we only have 2 categories. And we try to use the multiple linear regression model to fit this regression line, to get this regression line. But by looking at this regression line, we find some kind of problem. So the problem is actually here. So some part of the regression line is actually out of the range of 0 and 1. So out of 0 and 1. So in this case, for instance, we have some part of the regression line which is actually negative, but the response variable can never be negative. So in this case, this regression line seems not that appropriate. So that's our motivation to propose some new modeling. So here, using the classical regression line can result in some negative values you can consider it as the prediction or the fitting of the response variables. So that seems to have some problem. And also we can analyze the problem in more details by using this violation of linear regression assumptions. So if we have y as our response variable and x as the time, so firstly we can have these 3 violation of linear regression assumptions, and I summarize these 3 here. So the first one is obvious. So firstly, y is not from the normal distribution, obviously, because we can only have 2 values. But for the normal distribution, we always have continuous values in a range. So in this case, firstly, the normality assumption is not satisfied for this kind of data set. And secondly, let's compute the mean for each category. So now we introduce some new function which is called the t-apply. So what's the meaning for this t-apply? So this t-apply computes the mean, actually the sample mean of response so you need to look at, so it computes the sample mean of the response, so we put response here in the first argument of this function. However, we compute the sample mean of response by time. So we consider given different time, so that's our second argument. And the third argument is exactly what we want to compute. So basically, this function realizes the idea we have used here. So this idea, given some specific value of x, we want to compute the sample mean of y. This idea can be realized by use the t-apply function on page, so what's the page number? The page number is 8. So if you still remember the procedure by using our hand, so now we actually can use the R function to help us to obtain it directly. So what's the meaning here? So that means, let's look at this 1.25. Let's look at our output. So that means when x equals to 1.25, the sample mean here is, the sample mean is 0.857, which is exactly 6 divided by 7. So that's exactly the result by using our hand, I think, in this page. And also we can compute the other kind of situation for x. Here, given x equals to 1, the sample mean here is 0.8. And we can keep on looking at that, and we can have this kind of conclusion. So the sample mean of y here, given different kinds of situation of x, we can have different sample mean of y. But if you still remember, the sample mean here is actually the proportion that y equals to 1, which is from our previous computation by hand. So in that case, those sample means, you can also observe it. Those sample means should be in the interval of 0 and 1. Right? So that's our observation. But we actually transform our observation here in our code and also our output. And remember that for the multiple linear regression model, we actually model the mean of response as a function of the explanatory variable. Remember? So for the multiple linear regression model or the simple linear regression model, we model the mean of response as a linear function of the explanatory variable x. So in that case, because we have this kind of function form, beta 0 plus beta 1x, so basically, if we have this form, we can always have this mean can be in the range from minus infinity to infinity, because it's a straight line. So what's the meaning here? If you look at this straight line function, so you can look at the straight line function here. So for a straight line function, we can always have the range from minus infinity to infinity for a straight line. But for this kind of binary case, we always have our mean of response within this interval 0 and 1. We do not have minus infinity and plus infinity. So that means the range So the conclusion here is that the range of mean for binary response is within 0 and 1. But the problem here is that if we try to use the multiple linear regression model, we always get this minus infinity to infinity. So we do not have a match for the range if we use the multiple linear regression model on the binary response variable. So the second problem is really a problem here, because we do not have a match for the range of the mean of response. And also we can look at the third variable, the third problem, so not the third variable. So I think in the second procedure, we compute the mean of response by time. So here we can also compute the variance of response by time. Computes the variance of response by time. So variance is here, and response is here, and time is here. So in order to use this function, you need to know what you are computing. So what's the meaning here? So that just means, for instance, in this case, given x equals to 1.25, the variance of y here is 0.143, the sample variance. So given some specific value, we can get the sample variance. So by observing this kind of results from R, we can find that the constant variance assumption is violated, because given different values of x, we always have different values of the variance. So in conclusion, we have these three problems. The first problem is that y is not from the normal distribution. The second problem is that the range of the mean for this binary response is within 0 and 1, which is not from minus infinity to infinity in the multiple linear regression model case. And the third problem is that we do not have the constant variance assumption for the binary response variable. So for these three problems, the third problem, the constant variance assumption problem, can be fixed by using the weighted regression. We have talked about it. So for the first problem, it's not normal, but the least square estimation sometimes can also be used for the non-normal distributions. So this is also not a very serious problem. But the problem 2, which is actually from our observation, the different range for the different range of 0 and 1, and also minus infinity to infinity, which is exactly the problem if we use the multiple linear regression model for the binary response variable. So that's our motivation to propose a new model to get a match for the binary response variable mean within this 0 and 1, and also our regression equation. So this is our regression equation. So how can we do that? So in order to solve this kind of problem, the problem here is that for this binary response variable y, so if we have the binary, y, we always have the mean of response in the interval 0 and 1, because the mean of response usually means the proportion of y equals to 1. So, but for the linear regression model, this is our linear regression model, it can takes the value outside of 0 and 1, and usually minus infinity to infinity. So how can we solve this kind of problem? And the idea is actually not that hard. The idea is that on the left side of the equation, the mean of response is within minus 1, not minus 1, 0 and 1, right? And on the right side of the equation, beta 0 plus beta 1 x can be from minus infinity to infinity. So how about we just add some function? We consider some bridge. We add some function to force the right side of the equation is within 0 and 1. So that's the idea. So what kind of function can do that? So I can give you some example of this function. So the example here is hv equals to e to the power v. So that means the exponential of v divided by 1 plus e to the power of v. So this function is exactly within 0 and 1, and it can transform anything between this minus infinity to infinity into this 0 and 1. So in that case, we find we can use some function to force the right side of this equation within 0 and 1. And in that case, we will have a match for the mean of response and also the regression equation. So that's the idea for this generalized linear modeling. Because we do not have a match, then we find some bridge to match the left side and also the right side of the equation. And then now we can propose, so what's the exact modeling for this generalized linear model? So usually we can consider this function h has an inverse function. So how to compute the inverse function? So what you can do here is, for instance, if we have the function hv, so you can let hv equals to u, and then you can solve v. So if you solve v here, v should equals to log u divided by 1 minus u. So this log here is actually the inverse function. So this is our h inverse u. So if we have the inverse function, then we can try to consider the inverse of two sides of this equation. So consider h inverse of the left of the equation and h inverse of the right of the equation. And because here we have the inverse and h inverse and h, so basically we have they are eliminated. So in that case, we are going to have this beta 0 plus beta 1x, which is something we feel familiar with in the multiple linear regression model. And if we write g function as this inverse function, and then we can just rewrite this equation. So we write it from the right side and also the left, from the right side to the left side. So we just put this beta 0 plus beta 1x here equals to this h inverse, the mean of response, and at last it equals to this g function of mean of response. So this g function is, remember that it's exactly the inverse function of this h. So what's h? H is some function to force the right side of the equation within 0 and 1. So this is exactly our generalized linear model form. So we can officially propose our generalized linear model form. So we give some intuition. I understand that you may need some time to process it, but now let's look at what's the meaning for this generalized linear model. So remember our multiple linear regression model. The multiple linear regression model is just to model the mean of response as a function, as a linear function of the explanatory variable, right? So that's our multiple linear regression model. And the generalized linear model here is that the only difference is this g function. So we just put a function to impact on the mean of response, and we consider a transformation of the mean of response still as a linear function of the explanatory variable. So that's the generalized linear model. And the purpose of this g function is actually to solve this in-match or this not matching problem for the mean of response and also this linear combination. So that's the incentive for us to propose this g function. And this g function is called the link function. So that's the only difference between the generalized linear model and also the multiple linear regression model. And this G function actually depends on different types of different response variable. And here, for this binary response variable, we can have this G function in this way. So that's the link function for the binary response variable. So that means if we have other types of Y, so we may have a different G function. So that means this G function, so if we have a different type, so if we have different types of Y, we should have different G function. And I think in the later lecture, I'm going to talk about the count response. Why? So what's the meaning for count response? For instance, how many students show in this lecture theater? So, for instance, if we have this kind of 0, 1, 2, 3, 4, 5, this kind of count response, we are going to have a totally different G function, but still we call this modeling generalized linear modeling. So the modeling is exactly the same, but we have the different link function. But in today's lecture, we only talk about this specific G function, which equals to log U divided by 1 minus U. And we are going to use it for the category response variable Y. And if we consider this specific link function and also this kind of generalized linear modeling, and then we can call it binary logistic regression model, and I will explain how this logistic termination is from. So for other GLM, I have already mentioned, the model is still the same, but the problem is that we have different G function. So that's the generalized linear model. So basically, in today's lecture, I only use this binary logistic regression model as an example to explain what's the meaning for this generalized linear model. But still, we have this abstract definition for the generalized linear model. And I think in the later lectures, you may feel more familiar with that based on the other examples, because now you only have one example. So let's take a 10 minutes break, and then we are going to talk more details about generalized linear model in this case. Okay, let's start the second half of today's lecture. So firstly, let me use one sentence to summarize the reason why we need to propose the generalized linear model. So the reason here is that the incentive to propose GLM is to solve the mismatch problem between mu y given x equals to x. So that is the mean of response. So the mean of response and when y is a binary variable, the mean of response y given some specific value of x is within 0 and 1. Between mu and our linear regression line, beta 0 plus beta 1 x. And the range is from minus infinity to infinity. So this is the mismatch. So the incentive to solve this GLM, to propose the GLM, is actually to solve this kind of mismatch problem of the between the range of mu and also the range of this straight line. So that's the incentive. So in order to solve this mismatch problem of these two ranges, so what we propose here is that we try to consider some function g such that the range of these two are consistent. The ranges of these two are consistent. So that's the idea for this generalized linear model. So that's the only difference between the multiple linear regression model. So later you will find a lot of similarities, but the most important difference here is that for the GLM, we have an extra function which is called g. And also for this g function, different types of the response variable. For instance, today we talk about binary response y, but later we are going to talk about the counter response y. So if we have different types of response variable, we are going to have different function of g. So that's the only difference between different generalized linear model. And later you will see more examples, so I think you can understand it more. But in today's lecture, I think basically we have this, what we have talked about in this course and what we are at in today's lecture. So we have talked about the, for the continuous response, we can use the multiple linear regression model and also indicator variable to help us to solve the continuous response regression problem. And for this two category response variable, we need to use our new modeling, which is called binary logistic regression model, which is actually a special case of GLM. And also, in order to, sometimes we also have the categorical variable as our explanatory variable. So in that case, we still need to use the indicator variables to help us to solve the problem. And the idea to use the indicator variable is exactly the same in the multiple linear regression model. So we are not going to talk about it in details. So if you have any doubt in these indicator variables, my suggestion is just to review the part in the multiple linear regression model, and everything keeps very similar for this binary logistic regression model. So I think that's the introduction and the motivation for the binary logistic regression model and the generalized linear model. Any questions so far? So I think the most important thing is this one sentence, to solve this mismatch problem between different ranges. So that's the key for this, key to propose this generalized linear model. Any questions? Okay, so now let's officially talk about what's the meaning for this binary logistic regression model. You will find that there are a lot of details in this model assumptions. And I think do not be afraid of it. So the reason why you find it not familiar here is that you are not familiar with the discrete distribution. I think you are more familiar with normal distribution. But for this discrete distribution, I think you need some time to process it, but I will try to explain it more clearly. So if you still remember the multiple linear regression model assumptions, the first one is, I do not remember, but I think there is one which is the normal distribution assumption. But in this case, because we only have y, y can only take two values, 0 and 1, so y can only take two values. Y takes 0 or 1. So in that case, we no longer have the normal distribution, but we have this Bernoulli distribution. So you may feel a little bit not familiar with this distribution, but that's fine. I will explain it in details. So consider that we give some value of x. So that means x, we give some specific value like x1 equals to 1 until xk equals to 3 or something like that. We consider our response variable given those values of, after given those values, our response variable follows a Bernoulli distribution. So that means, what's the meaning for it? So that just means given some value of x, y can only take two values, 1 or 0. And then for this Bernoulli distribution, we need to specify the probability of 1, y equals to 1, and the probability of y equals to 0. So here we just consider given some specific value of x. So this probability should depend on x. So that means for this Bernoulli distribution, so what's the meaning? So that just means y can take two values, 1 and 0. The probability for y equals to 1 here is pi x. And the probability that y equals to 0 here is 1 minus pi x. So that's the meaning for this Bernoulli distribution. Bernoulli distribution just means we can only take two values, 1 and 0, and for each value we have a probability. And because we consider the case given x, so this probability depends on x, so we use this pi x to represent the probability. And this probability is within 0 and 1 because it's a probability. And also, based on this pi x, we can compute the probability that y equals to 0. So what's the probability of y equals to 0? So that's 1 minus the probability that y equals to 1. So in that case, we have 1 minus pi x as the probability that y equals to 0. So that's the probability. I think you can consider it as the direct probability formula to compute the opposite of y equals to 1. And after we define the probability, we can compute the mean. So what's the mean? Mean here is actually for the discrete variable, if you still remember how to compute the mean of this discrete variable. So compute the mean of it. So the mean of the discrete variable just equals to 1 times pi x plus 0 times 1 minus pi x, right? So that's how to compute the mean of this Bernoulli distribution. And after this computation, we can obtain pi x, which is exactly equal to the probability. So that's something we observe, I think, in our early example. Mean of binary equals to probability. So that's the reason why we need to consider the range of the mean within 0 and 1. So that's the first assumption, Bernoulli distribution assumption. Any questions about this assumption? So let's look at the second assumption. Because the mean of response here is within the range 0 and 1, right? So we need to consider, however, the linear combination here can be from minus infinity to infinity, right? So in order to match these two, we just add a link or add a bridge, which is called the link function g. We add this g such that on the left side of the equation, we also have the minus infinity to infinity, and on the right side of the equation, we always have minus infinity to infinity. So this g function here can actually be found, which is called the logit link. So it has a name, it's called logit link. So this is exactly the function which can force this mu y given x and then the g function from minus infinity to infinity. So gu equals to log u divided by 1 minus u. So it can change the range on the left side of the equation. So that's the idea for the generalized linear model. And it's called generalized linearity. So the difference between this generalized linearity and also the linearity in multiple linear regression model is this g function. And for the other things, they are basically the same. So that's the second assumption. Any questions? The only difference is the g function. So we also need some remark to help us to understand it more. So we can consider the inverse of the logit link function. So we have the g function here. So that's the g function, gu equals to log u divided by 1 minus u. So we can also try to solve the inverse function. So how to solve the inverse function? What you need to do here is just to put gu equals to v and then solve u. And then you can obtain log u divided by 1 minus u equals to v. And then you can solve u just equals to e to the power v divided by 1 plus e to the power v. And that's our inverse function. So I think this is not the only, but I think the normally used two functions, the logit function and also the inverse of the logit function in this course. So what you need to do here is just to know this is the inverse function. And this inverse function has a name, which is called the logistic function. So that's the reason why it is called binary logistic regression, because the inverse of the link function here actually has a name which is called logistic function. So for the property of this logistic function, the logistic function is within 0 and 1. So that's the reason why we use this link function, because the inverse of the link function is actually within 0 and 1. So remember the generalized linearity. The generalized linearity means g of mu y given x equals to beta 0 plus beta 1, x1 plus so on and so forth plus beta k xk. So by using the inverse function, we can obtain mu actually equals to g inverse those linear combination. And because this g function is within 0 and 1, always within this 0 and 1, so we can make sure that this mean of response is always within 0 and 1. And remember that the mean is equal to probability. So we can make sure that the probability is within 0 and 1. So that can make everything consistent. But remember this, because later we are going to use it to get our fitted probability or the or the predicted probability. So remember here, so we are going to use the mean of, so we are going to use this generalized linearity to obtain our probability, because the probability just equals to the mean in this binary case. And the last one is the independence assumption, and I think that's basically the same to the multiple linear regression. So in conclusion, the most important thing is this generalized linearity. And also later we are going to use this another form, so you can consider it as another form of the generalized linearity in our in order to obtain the probability here. So remember this formula, and later we are going to use it again. Any questions? Now, let's just use the formula to obtain the probability. So remember that we use pi x to represent our probability, and also the meaning for pi x here is the probability that y equals to 1 given x. So here we actually have a lot of notations to represent the probability. We have the pi x, and also we have the, so basically it's just the direct explanation of the probability. And also, based on the property of the Bernoulli distribution, the mean is also equal to the probability. So remember that in this binary case, we have a lot of notations to represent the probability. And the probability equals to the G inverse, the linear combination. And this is directly from here, the G verse of the linear combination. And it just equals to, if we just put G inverse here, we plug in G inverse. So G inverse U just equal, not U, I think it's V, equals to EV divided by 1 plus EV. So just put those linear combination in V, and then you can compute the probability. So this is exactly the probability that y equals to 1 in this binary logistic regression model. We are interested in this probability because later, I think here, we are going to use this probability to interpret the model. So what's the meaning for the model? And in order to interpret the model here, we introduce some new concept which is called odds. So what's the odds? So the odds is equal to the probability of y equals to 1 divided by 1 minus probability that y equals to 1. So that's the meaning for this odds. And we call it odds that y equals to 1 given x. And based on this definition, we can actually plug in those probability and then obtain the exact expression of these odds. So this is the expression. And the expression is the exponential of those linear combination. So now let's look at why we need to introduce these odds. So firstly, what's odds? So I use these 3 examples to explain to you what's the meaning for odds. And actually, I think in the Western history or in the gambling history, I think a lot of people like to use odds instead of probability or chance. So odds equals to 1 just means there is a 50 chance that y equals to 1 will occur. So you can just plug in the probability that equals to 0.5, and then you will obtain odds equals to 1. So that means if you have a 50-50 chance, sometimes you can say that you have the odds equal to 1. So you can consider it as another word of probability, but we just consider it as a new concept to represent the probability. So if we have a large odds, usually it just means that we have a large probability that something will happen. If we have a smaller odds, so that means we have a smaller chance that something will happen. So in other words, odds is just another way to describe the probability. So after introduce this concept, let's look at how to interpret this binary logistic regression model. So for this binary logistic regression model, so firstly, let's compute 2 things. So let's firstly compute odds that y equals to 1 given x1 equals to x1 plus 1 and x2 equals to x2 until xk equals to xk. So this odds should be equal to this probability divided by 1 minus probability. So here we consider those, basically we consider the control variable idea. So that means we control the other variables x2 to xk, but we change the first variable x1. And then we can obtain the odds at this case, and this is the odds result based on this model. And also we can compute the odds that y equals to 1 given x1 equals to x1, but we keep other variables the same. And also we can obtain another odds. So the only difference between these two odds here is the exponential of beta 1. So that's from the computation result. That's not from our imagination. It's actually from our assumptions and the logic. So because we have this difference exponential of beta 1, so we can have the interpretation of the coefficient in the binary logistic regression model. And this model, the interpretation is different, and you should be careful about it here, because the interpretation of the model is always very important. So what's the interpretation? So the interpretation here is that if we control the other variables, if x1 is increased by 1 unit, so that's increased by 1 unit, then the odds that y equals to 1 will change by a multiplicative factor of exponential of beta 1. So that's exactly from this derivation. So later when I ask you to interpret beta 1 in binary logistic regression model, in this binary logistic regression model, so you always need to interpret in this way. So that's from the assumptions. And basically, because odds, you can treat odds as another way to say the probability. So basically, this beta 1 actually interprets the multiplicative change for the probability. You can consider in this way from intuition. But the exact or the accurate way to interpret it is the multiplicative change of the odds. Any questions for the interpretation? So the interpretation is totally different from the multiple linear regression model by involving this new concept odds. No question? Okay. So now let's look at the estimation. I think basically that's the most difficult part in today's lecture. So in order to obtain the estimation, so what we can do here is that because here we have a new model and also we only have 1 and 0 observation for y for the response variable. Response variable can only take 2 values, 1 and 0. So in that case, you can find that the least square estimation is no longer working. So we are going to mention another method which is called the maximum likelihood estimation. But in order to talk about this new estimation, we need to define something which is called likelihood, and then I will explain the reason why we do that is actually very sensitive and reasonable. So firstly, we are going to play with those probability again, because the likelihood function in this case is actually related to the probability. So consider the response variable y equals to small y. So the small y can be 1 or 0. So you can consider that small y is just another name of 1 and 0, but it can unify 1 and 0 in this case. So remember that here we define the probability y equals to 1 as pi x, right? So pi x equals to pi x to the power 1 times 1 minus pi x to the power 1 minus 1. So this equality is always equal, is always satisfied. And here, because in this situation y equals to 1, so we can just put y here, and then we will have this formula for this probability. And also, similarly, we can compute the probability of y equals to 0 similarly. And here, the probability of y equals to 0 equals to 1 minus pi, which is equal to the pi to the power 0 times 1 minus pi to the power 1 minus 0. And if we plug in y equals to 0 here, so we can replace 0 by using y, and also we can have this formula for the probability. So we can have a unified formula for the probability, in this case, for this binary logistic regression model case. So in that case, small y can be 0 or 1. So it doesn't matter because this probability formula can be for 0 and 1 both. And recall that, if you still remember, this is from the generalized linearity. The probability equals to the mean equals to the G inverse of those linear combination. So in this case, in order to simplify the notation, we call it the probability with the parameters beta 0 to beta k. So that means this probability depends on those parameters, right? And also, we introduce more notations, which just helps us to derive the likelihood later more easily. So remember that we actually have k variables. So we can actually write this equation into more details. So we can just actually put more variables here. So it is another way to write this probability equation. And also here, because we have this P is also our probability, so we have this way to write our equation. So we have different ways to write this probability. So that's just some notations. And remember this notation, and then we are going to derive the likelihood. So after we talk about the probability of, basically you can consider it as the probability of the population. So let's look at the probability of different observations. So we consider the independent observations. So that means we have n observations for each variable of x, and also we have n observations of y. And for each observation, we can have the probability. So this is exactly the probability, which equals to the pi to the power yi. So yi just means the ith observation. And times 1 minus pi to the power 1 minus yi. And also we can write this probability as this form. So we just use some notation. It's the probability of observation I, and also those parameters are involved. So that's exactly the probability of y equals to yi, and the yi can be 0 or 1. And at last, we define the likelihood. So what's the likelihood? The likelihood is the probability that we observe y1 equals to y1 until yn equals to yn, given all axes. For instance, we can have y1 equals to 1, y2 equals to 0, y3 equals to 1, or so on and so forth, yn equals to 0. So if we observe this kind of observation, we can actually compute the probability that we observe this kind of observation given all kinds of values of x. So how can we compute this probability? So firstly, this probability can be represented by using it. So it's exactly the meaning of this probability. And secondly, because we have the independent assumption, so we can actually to split this probability into this product. So here just means we consider the product from I to n. So this means product. The product from 1 to n of the probability of each observation. And for each observation, we can compute the probability here. So you can see the conclusion here is that this probability or this likelihood function is actually a function of beta 0 to beta k. So I think that's the important conclusion. So the likelihood is a function of beta 0 to beta k. And this derivation, I think, is the most difficult part into this lecture. But the conclusion, I think, is more important. Just remember that what's the likelihood? Likelihood is just the probability that we observe, and it's usually a function of beta 0 to beta k. So that's the most important thing here. So because the likelihood here is the probability that we observe y1 to yn, so that's the probability. And the likelihood estimation, maximum likelihood estimation, actually has this very, maybe a little bit strange, but sometimes we can consider it as some kind of reasonable logic. So this logic here is that since we have observed this kind of situation, so in this case, there should be a pretty good chance that this observed outcome should happen. Otherwise, we cannot observe it, right? So in this case, because we observe it, so we consider the probability. So this is the likelihood, or it's the probability that we observe y1 equals to y1 until yn equals to yn. So we consider that those parameters, beta 0 and beta k estimation, should maximize this probability. So that just means that we actually should have a very pretty good chance that this observation will happen. So we actually maximize this probability and obtain our estimation. So those estimation beta 0 hat to beta k numerically maximize this likelihood function. And unfortunately, unlike least square estimation, we no longer have formula for this beta 0 hat to beta k. We can only have the numerical solution. But fortunately, R can help us to do that, to obtain those estimations directly. So in that case, those estimations can be obtained by using R. So there is no formula for this estimation. But the logic here is still required. You need to think that for this kind of estimation, we actually maximize some probability, not some probability, the probability that we observe our observation. So that's the understanding of this maximum likelihood estimation. Any questions about maximum likelihood estimation? I understand the derivation is not easy, but the more important thing is about the conclusion and the idea, the brief idea behind it. Any questions? Okay, after we obtain the maximum likelihood estimation, so we can use R, and later I'm going to use some examples to tell you how to realize that. So the next step is usually to obtain the estimated mean function or the fitted probability. So remember the generalized linearity. So for the generalized linearity, we have G mu y given x equals to beta 0 plus beta 1 x1 plus so on and so forth plus beta k xk. So that's our generalized linearity assumption. So by using this assumption, we can compute the mu y given x. So if we consider this plug-in idea and by plugging the estimates, and then we can obtain the estimated mean function. So what we can do here is just to plug in those betas, estimation of betas. So this is exactly the same compared to the multiple linear regression model. The only difference here is this G inverse function. And also, we can obtain the fitted probability because the probability equals to the mean, and the mean equals to the G inverse, the linear combination. So what we need to do here is just to apply this plug-in idea and plug in those estimates, and then we can compute the fitted probability. So usually when we talk about fitted probability, those x's are from the training data set. But still, we can consider those x as some new data set, which can be considered as the test data set. And in that case, we are going to obtain the predicted probability, the forecast of probability here. So the formula for the forecast of the probability is basically the same compared to the fitted probability, but the only difference here is that we consider some new observation of x. So in that case, we can actually forecast. So by doing that, we can forecast the probability probability that y equals to 1 So if we can predict the probability of y equals to 1, we can also predict the probability that y equals to 0, right? Because we only have 1 and 0 two categories for the response variable. So the next question is that based on this forecast probability, what is the prediction of y? So if we have the probability, how can we obtain the prediction of y? So the prediction of y is 1 or the prediction of y is 0. So in order to do that, let's look at the logic here. So remember that we have the probability pi x as the probability of y equals to 1, and 1 minus pi x is the probability that y equals to 0. So if the probability of y equals to 1 is larger than the probability of y equals to 0, so equivalently, you can just put pi x here. Pi x is larger than 1 minus pi x. You can obtain, if the probability pi x is larger than 0.5, then obviously there is a better chance that y equals to 1 will occur, right? Because the probability of y equals to 1 is larger than the probability of y equals to 0. So if we have this kind of case, we can predict. The idea here is that predict y as 1, because y equals to 1 has a larger chance to occur. So that's the meaning here. So in that case, 0.5 is actually a threshold to help us to predict the response. So the conclusion here is that if we have our forecast of probability is larger than 0.5, then we usually predict our response as 1, otherwise 0. So that's the conclusion. Or equivalently, you can consider in this way, the prediction of y hat is actually, the prediction of y is actually the category that has the larger forecast of probability. So for instance, if we predict y hat nu equals to 1, so that is equivalent that the probability of y hat nu equals to 1 given x nu is larger than the probability of y hat nu equals to 0 given x nu. So I think it's the forecast of probability. Forecast of. This is also forecast of. So this is the exact idea for us to predict some categorical response variable by using the probability. So that's exactly the reason why we always talk about the probability, I think, in today's lecture. The reason why we need to compute all this probability is actually to help us to obtain the final prediction. And later, this idea will be used for the other prediction of the other categorical variable, but we will talk about it later. But remember this idea. Any questions? Okay, let's look at this real example and hope that by using this real example, you can understand it more clearly. So in order to use this binary logistic regression model to regress the two-category response variable on the experimental variable time, so we are going to use this GLM function. So the only difference here is we use a different function. And in order to use this function, firstly, you need to specify the family. The family here is called binomial. So why we use binomial? I think the reason here is that the Bernoulli distribution is a special case of binomial distribution. So just remember it, and I will not talk about details about what's the binomial distribution, what's the Bernoulli distribution. I think in this course, at this stage, I think just to know what's the meaning for the Bernoulli distribution. And when we talk about the binomial logistic regression model, and in that case, you will understand what's the meaning for the binomial distribution. So basically here we just mean that we want to use the Bernoulli distribution to represent the distribution of the response variable. And also we need to specify the link function. The link function here we use is the logit link. So in that case, we have our regression output. So this is our regression output. So by using this regression output, we can actually plot the fitted probability. So if you use these fitted values, so that actually obtain the fitted probability. So how to compute the fitted probability? It can be computed in this way, but R actually helps us to obtain this fitted probability automatically. So you can just plot this fitted probability in this plot, in this dashed line. So LTY equals to 2 just means we obtain a dashed line. So you can see that this probability is within 0 and 1. So in that case, that's good because we actually need it. Because the probability should be within 0 and 1. That's the most important conclusion in today's lecture. And also at last, we detach A. So what's the meaning for this detach A? Detach A just means that we no longer want to use A. So we don't want to use A anymore. So after you do that, you cannot use like time to call a variable, time, and you need to use $A time. So after you use detach A, you can no longer use time directly to call this variable, but you need to use the dollar to call this variable. So basically, it's opposite to attach A, if you still remember. So that's some details in the R code, but the more important thing here is that you can actually use R to obtain the fitted probability. So the second thing here is actually to obtain the prediction of a new variable. So let's consider that if we give a customer a new advertising time of 1.5 seconds, so we want to predict whether or not this customer is willing to buy this product after this exposure of the more advertising time. So what you can do here is that to use this data frame to define a new X variable. So that's exactly the same compared to the multiple linear regression model. And then what you need to do here is just to input so this is the GLM output, and also the new variable, new X variable here. And the difference here is that you need to specify this type equals to response. Because I think in the multiple linear regression model, you do not need to specify it, right? So if you specify this response variable, you will obtain a number. So this is the number, but actually it's not the forecast of the response, it's actually the forecast of the probability. So based on this probability, because this probability is larger than 0.5, so you should have a prediction of response as 1. So that means the prediction here is that this customer is willing to buy the product. And how to obtain this probability? You need to input the estimation of all the betas. And also you need to input the new X variable into this formula, and then you can obtain the probability. And those estimation of beta can be found in the summary output, and I will talk about the summary output of the generalized linear model later, I think, in my next lecture. So basically, that's the end of today's lecture. And any questions? Okay, if there is no question, so in the next lecture, I'm going to talk about the inferential tools and the variable selection for generalized linear model. So that means even now we only talk about one generalized linear model, but actually this topic can be applied for all the other generalized linear model which are going to be talked about later in this course. So it's a really you can consider it as a very large topic for all the generalized linear model later. So later, I'm not going to talk about the inferential tools and the variable selection for the other generalized linear model. We only talk about it once, and that's in my next lecture. And thank you so much, and see you on Thursday.